Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is using an oscilloscope to measure phase shift. Our objective is to learn how to use an oscilloscope to measure the relative phase shift between two waveforms displayed on the same horizontal time axis. We'll examine traditional manual calculation methods, as well as time-saving automated methods offered by some modern oscilloscopes. If you recall, at the very end of the AC Ohm's Law lecture, available at the Big Bad Tech channel, we learned that digital multimeters in AC voltmeter and AC ammeter mode are traditionally limited to measuring effective or RMS value only and do not customarily measure relative phase shift. Today we'll learn to experimentally measure relative phase shift between two waveforms using an oscilloscope. For the purposes of today's lecture, we'll be making use of the Tektronix TBS 1032B digital oscilloscope. This is in no way meant to be neither an exhaustive review of this tool nor an endorsement of this particular manufacturer or model. I only wish to present the functions of interest on a representative example so the viewer can gain some practical exposure to these functions and interpret the manner in which results are displayed. If you recall, an oscilloscope is a graphical means of displaying voltage as a function of time, where voltage is the vertical dimension and time is the horizontal dimension. By properly scaling, positioning, and triggering an individual waveform under inspection, various properties about that individual waveform can be measured, including but not limited to peak, peak-to-peak, effective or RMS value, period, and frequency. In addition to these properties related to individual waveforms, modern oscilloscopes like the Tektronix TBS 1032B digital oscilloscope are often multi-channel devices, meaning they can simultaneously display two or more voltage waveforms on the same screen. This ability to simultaneously depict more than one waveform conveniently lends itself to measuring the relative phase shift between the waveforms under inspection. Let's examine the means of measuring relative phase shift using traditional manual calculation methods first. Manual calculation, in contrast to the automated methods I'll demonstrate in a moment, are open to some interpretation. However, the values obtained should be close to your anticipated results. While admittedly primitive, these techniques are absolutely essential to the conceptual understanding of oscilloscopes and AC circuit theory and are not to be dismissed. You never know when someone might ask you to do this on a quiz or an exam. Hint, hint. Manual measurement using an oscilloscope is really just a game of unit conversion. The advantage being, given vertical and horizontal sensitivity are independently adjustable, a user has a degree of control over the conversion factor. Additionally, given a trace can be repositioned left, right, up, and down in the oscilloscope screen, a user can take advantage of various markers to obtain more accurate results. Since today's lecture deals exclusively with measurement of the relative phase shift between two waveforms, our principal dimension of concern is the horizontal time axis. Although, as we'll learn in a moment, rescaling the vertical axis can sometimes increase our precision. You'll note this oscilloscope is currently scaled using a vertical sensitivity of 2 volts per division on both channel 1 and channel 2. Additionally, it has a horizontal sensitivity of 500 microseconds per division. You note within each vertical and horizontal division, 5 subdivisions exist, where each subdivision represents 1/5 of a full division. Given the current vertical sensitivity, each vertical subdivision represents 1/5 of 2 volts, or 0.4 volts. Similarly, given the current horizontal sensitivity, each horizontal subdivision represents 1/5 of 500 microseconds, or 100 microseconds. When a sinusoidal voltage waveform is displayed on channel 1, we can use the scaled vertical and horizontal markers to measure various properties. By all means, pause the lecture and see if you can determine the peak value, the effective value, the period, and the frequency of this waveform. If you're tracking, you should have obtained the following values. Looks like this first waveform in yellow peaks at, let's say, 3.6 divisions above the horizontal axis. Given the current vertical sensitivity of 2 volts per division, this corresponds to a peak value of 3.6 divisions times 2 volts per division, or approximately 7.2 volts. This peak value corresponds to an effective value of 7.2 volts over square root 2, or roughly 5.1 volts. You'll note this sinusoidal waveform isn't perfectly symmetric in that its positive peak is slightly larger than the negative peak. However, let's just go with these figures. Note the 2 zero crossings going positive appear to be separated by, let's say, roughly 6.7 divisions. Given the current horizontal sensitivity of 500 microseconds per division, this corresponds to a period of 6.7 divisions times 500 microseconds per division, or approximately 3.35 milliseconds. It can be demonstrated that by taking the inverse of this measured period value, that our frequency is 1 over 3.35 milliseconds, or approximately 298.5 hertz. The astute and observant among you may have noted that the oscilloscope has already gone to the trouble of performing this calculation and is displaying a frequency of 299.2 hertz, essentially 300 hertz, in the lower right-hand corner. Key to the measurement of phase shift is your understanding that a sinusoidal waveform undergoes a complete cycle in 360 degrees. Given this waveform has a period of 3.35 milliseconds, it can be rightly said that 360 degrees equals 3.35 milliseconds, and this conversion factor establishes a means of translating between time and degrees and vice versa. Let's put these figures aside and do the same thing for a second waveform on channel 2 in blue. Multi-channel oscilloscopes allow a user to toggle between channels or to display both waveforms simultaneously. Here I've turned off channel 1 and turned channel 2 on. You note the oscilloscope is still scaled as previously using a vertical sensitivity of 2 volts per division and a horizontal sensitivity of 500 microseconds per division. By all means, pause the lecture and see if you can determine the peak value, the effective value, the period and frequency of this second waveform. If you're tracking, you should have obtained the following values. It looks like the second waveform in blue peaks at, let's say, 1.8 divisions above the horizontal axis. Given the current vertical sensitivity of 2 volts per division, this corresponds to a peak value of 1.8 divisions times 2 volts per division, or approximately 3.6 volts. This peak value corresponds to an effective value of 3.6 volts over square root 2, or roughly 2.5 volts. Despite being shifted from a primary division, note the two zero crossings going positive still appear to be separated by roughly 6.7 divisions. Given the current horizontal sensitivity of 500 microseconds per division, this again corresponds to a period of approximately 3.35 milliseconds. It can again be demonstrated that by taking the inverse of this measured period value, that our frequency is approximately 298.5 hertz. This is the same frequency we obtained for our first waveform. Again, note the oscilloscope has already gone to the trouble of performing this calculation and is displaying a frequency of 299.3 hertz, essentially 300 hertz in the lower right-hand corner. Let's put these figures aside and discuss relative phase shift. To manually calculate the relative phase shift between these two waveforms, one needs to display them simultaneously. To do so, both channel 1 and channel 2 are turned on. Note both channels are displayed using a vertical sensitivity of 2 volts per division and a horizontal sensitivity of 500 microseconds per division. It is immediately evident the yellow waveform on channel 1 is larger than the similarly scaled blue waveform on channel 2 due to the properties we previously measured. One can also make two equally relevant observations about these waveforms in terms of phase shift. Note the blue waveform on channel 2 appears to lag the yellow one on channel 1. Similarly, one can also state that the yellow waveform on channel 1 leads the blue waveform on channel 2. This duality is inherent to the relative nature of two waveforms in that one can only describe a repetitive waveform's position with respect to another. Relativity, as the name implies, relates two quantities with one another, and importantly implies that one of the pair is used as a frame of reference from which the other is measured. Let's just assume the yellow waveform on channel 1 is our reference, and we wish to determine the phase shift of the blue waveform on channel 2 with respect to the yellow waveform on channel 1. The phasor representation of the yellow waveform on channel 1, since it's our reference, is 5.1 volts at an angle of 0 degrees. Note the zero crossing going positive of the blue waveform appears to lag the yellow waveform by 0.6 divisions. Given our current horizontal sensitivity of 500 microseconds per division, this corresponds to a time shift of 0.6 divisions times 500 microseconds per division, or 300 microseconds. Now we need to convert this time shift to degrees. Given both these waveforms complete a 360-degree cycle in 3.35 milliseconds, a unit conversion shows that the blue waveform on channel 2 is lagging the yellow waveform on channel 1 by 300 microseconds times 360 degrees divided by 3.35 milliseconds, or approximately 32.2 degrees. The phasor representation of the blue waveform on channel 2 is therefore 2.5 volts at an angle of negative 32.2 degrees. In summary, there is a relative phase shift at 32.2 degrees between the two waveforms. Given this phase shift is relative, it can be said that the blue waveform lags the yellow waveform just as easily as it can be said that the yellow waveform leads the blue waveform. Now, both these channels of the oscilloscope are currently scaled using a vertical sensitivity of 2 volts per division. While this level of magnification does permit display of the complete waveform and easy measurement of properties like peak value and period, one can zoom in to gain an enhanced perspective of just the relative phase shift between these waveforms. If we change the vertical sensitivity of channel 1 to 500 millivolts per division, notice the top of the first waveform in yellow disappears off the display. However, the zero crossing going positive is crisper and far more recognizable. Note the crossing doesn't actually happen at a primary division like I assumed it did earlier. This may have induced a tiny error in our previous calculation. One can horizontally reposition the oscilloscope display to place the zero crossing going positive of the yellow waveform right on a primary division. Note I have not changed the magnitude of the first waveform in yellow. I've just rescaled it. The second waveform in blue looks comically small because it's still using our previous scale of 2 volts per division. If we change the vertical sensitivity of channel 2 also to 500 millivolts per division, again notice the top of the second waveform in blue disappears off the display. However, the zero crossing going positive is crisper and far more recognizable. Despite the increased ease of measurement using this rescaled display, it looks like the two waveforms are still separated by 0.6 divisions. Given our horizontal sensitivity is still set to 500 microseconds per division, this still represents a phase shift of 32.2 degrees. In an effort to increase the precision of the phase shift measurement, one is also free to adjust the horizontal sensitivity. However, this often necessitates a user horizontally reposition the display to keep both zero crossings going positive on the screen. If we change the horizontal sensitivity to 100 microseconds per division, notice the two waveforms are now separated by, let's say, 3 divisions. Given our horizontal sensitivity is set to 100 microseconds per division, this still represents a time shift of 3 divisions times 100 microseconds per division, or 300 microseconds. As previously, a 300 microsecond time shift inside a waveform with a period of 3.35 milliseconds has a phase shift of 32.2 degrees. Using this increased level of magnification, we still arrived at the same result. However, if there was any doubt previously, it's most certainly been dispelled. Again, note when rescaling to such a comical degree, it's often necessary to horizontally reposition the display so both zero crossings going positive remain on the screen. If you're too zoomed in or too zoomed out, you'll often get a distorted view of what you're actually looking at.